Okay, let's talk about the feature control frame for a straightness tolerance. Um, Straightness tolerance symbol and a tolerance value included. Here's an example. We got a straight tolerance symbol and the tolerance values included. The symbol indicates required tolerance zone shape. Here's my required tolerance zone shape. And I'll tell you right now, when I have a required tolerance zone shape like this, I'm probably talking about applying this to a feature of size, a cylinder, if you will. The value indicates the allowable size of the tolerance zone. The diameter symbol is only needed for cylindrical features of size. Material condition modifiers applicable only for features of size. And we never ever include a datum feature reference in a straightness tolerance. Okay, so I keep emphasizing here that the straightness tolerances can be applied to surface elements or they can be applied to features of size. So let's explore straightness applied to surface elements first. So what we're going to do is we're going to do this when the required form control is smaller than the size tolerance. If you need something to be straighter than what would be allowed by the maximum material boundary perfect form envelope, if you need something better than that, you need to apply a form control with a smaller tolerance than your sizes. Material condition modifiers are not used with form tolerances applied to surfaces. Okay, when we talk about surface elements, we talk about applying these form tolerances to surfaces. MMC is not a factor when we talk about applying surfaces. Size variation may limit usable form tolerance to less than the value specified, and then the form tolerance larger than the size tolerance only when independency symbol is applied to the size dimension. Here's how we would apply a feature, a flatness of a surface feature in a model. We would have the annotation plane like we're seeing here, and then we'll put the dimension on there, and then we'll put the straightness. Now notice how we put the direction of the straightness here. Very important. Okay, so the feature control frame is applied with a leader like this. Its represented line element shows direction. That's this here. Line element shows directions, and all annotations are on the same plane. If we were applying that to a orthographic view, for instance, the feature control frame would be attached by an extension line like this, or a leader like that. The line direction in the orthographic view indicates the tolerance line element direction. Okay, now what that means here is I'm in this view right here, I am assuming that my direction for the straightness goes in the same direction as dictated by the view. If you had put this line over here, it would be line elements in this direction. So, but this one is line elements in this direction. This feature control frame is applied to line elements in this direction. Straightness model for surface elements in models. Okay, so a cylindrical surface element here, again, it's applied with a leader, it's applied with a directional line, and then we'll have our feature control frame with our characteristic and our size. No diameter symbol because we're dimensioning a surface, not a feature of size. And here's what that would look like on a drawing, on an orthographic projection. We would have an extension line with our feature control frame, or we can have a leader with our feature control frame. And again, the direction is dictated by the view that we're showing. Okay, so in this particular view, our surface line elements are in this direction. Okay, so what does that mean? Straightness of line elements on a cylindrical surface. What does that mean? Here we have our perfect form boundary of 880. We have our min dimension here of 870. We have a derived median line based on that, and then each line element as in 6 thousandths max. Okay, so that's what this tolerance means. So 875 plus or minus 5 with straightness. So what that means is we have 6 thousandths straightness here for all of these line elements here based on this derived median line. That's what the straightness tolerance means in a cylinder for surface. Now, how will we verify surface straightness? Okay, so in one of the ways to do it is part set on an inclined sine bar, and a dial indicator is moved along the surface. The direction of movement is defined by the represented line element in the model from the orthographic views. So the direction is important. And then what we'll do is we'll check the full indicator movement. So let's talk about that for a second before I come back to the other one. So this is kind of what it would look like. I have a angled surface here with a surface form tolerance here of straightness. Okay, how would I check that? I would have a workpiece. I would put it on a sine bar such that this surface here would be horizontal, perfectly horizontal on my surface plate. And then I would move a dial indicator in this direction only over that surface, and then I would measure what the full indicator movement would be, and as long as that full indicator movement was less than 9 thousandths, then the part would meet the straightness tolerance requirements. Another way to do that is if you used a straight edge on a surface and then try to stick a feeler gauge underneath it. For instance, if you had a 6 thousandths tolerance, what you would do is you would put the part laid on a flat surface plate, and you'd get a shim stock that would be 6 thousandths, and you'd see if you can get it underneath that part anywhere. If you could, then the part doesn't meet the requirements. Okay, so that would be the other way to check those. Let's go again. Noted exceptions to Rule 1. Functional design determining the factor and deciding if you're going to use the exception. And to do this, you're going to show an independency symbol just like this. Okay. On the size dimension, independency symbol would be applied to the size dimension. Independency means that no perfect form boundary for the feature. Okay, so what can happen here is if you had a gasket or something that's wavy like that, okay, and you had the straightness, then it could theoretically be out because your part is wavy. Form is unaffected by the size tolerance, and form may vary outside the perfect form boundary. That's important for independency. The form may vary outside the perfect form boundary. And then the form tolerance may be larger than the size tolerance in this particular case. So in this case, I've got plus or minus 3 thousandths for this part here, but I'm allowing a flatness up to 10. Okay, and then what I'm saying is that that's an independency right here because the form tolerance is a lot larger than the size tolerance. So that's what that means. Okay, so we've talked a lot about surfaces. Now let's talk about applying that form tolerance, this straightness tolerance, to a cylindrical feature of size. Okay, we talked about surface elements. Now let's talk about features of size. So here's how you would apply it in a model on an annotation plane. You put the diameter, and then you put the feature control frame directly underneath the feature of size, the dimensional callouts for that feature of size. That's how you know that this feature control frame applies to a feature of size and not a surface. So the form tolerance feature control frame adjacent to the dimension or attached to the dimension line. Okay, that's two ways you do it. You could attach it to the dimension line, or you could place it underneath your dimension. The diameter symbol precedes the tolerance value. Yes, because that's a feature of size, it's cylindrical. Rule number 1 does not apply now that we've applied the form tolerance. It's assumed to apply RFS unless otherwise shown. In this case, we showed the MMC modifier, but it's assumed to apply RFS. That's rule number 2. I would like to stop this movie here. We're getting a little bit long. Thank you.